Hello everyone, this is a video that's going to walk through a brief overview of Worksheet 3 from our energy packet. We started this in class with, I believe, 1A and 1B, and we walked through the importance and the ins and outs of using these bar graphs to help track our energy, to help create our quantitative energy conservation. So we're still looking at a qualitative approach, meaning no numbers. But that will come soon enough. So I'm going to start with question 1C. So we're looking at the same system as problem 1A. So we're going to include everything. We're going to include the spring, the track, the cart, and the earth. So we're not excluding anything. So that's a good sign that we're not really going to have to worry about work. We're just tracking all the energies. So we see in the beginning, it's just all elastic, all 5 units of elastic potential energy. And then at position B, we're now moving. So we have kinetic and gravitational, just like part 1A. But now there's friction between the track and the cart. So anytime we see friction, there's going to be some energy lost or transferred to thermal energy. So that's where we get our bar graph over here. So we still have probably the most gravitational potential energy because we're stored high above the ground. Still moving, which is by our little whoosh marks there. Some kinetic and some thermal. The relative sizes of these bars, again, is relative. We don't have specifics. I just put what I thought would probably happen in real life. Thermal probably going to be the smallest, but just to keep for easy math, I had it as a 1. So we have a total of 5 units in all of our bars. And then that helps us make our conservation of energy equation where we're in the beginning, we're starting with all elastic, and then that's going to be broken up into our 3 different types. For 1D, we're now looking at same system, same situation, but we're just not as high up here. So this, if you've ever ridden a roller coaster, the higher and higher you go, the slower and slower you go. So we have 5 units of energy in the beginning, converted into kinetic and gravitational. So I just wanted to show it a little bit different from the other bar graph from 1C. So here we probably have more kinetic and less gravitational as compared to the previous problem. And no friction, so we're only going to have our kinetic and gravitational in the end. New problem, question 2. We have a car rolls up a hill until it stops. So we're shown this with our picture saying that our position on the y-axis is starting at 0 and then something greater than 0. So we're going vertically upward. And velocity-wise, when we start observing, our velocity at position A is greater than 0. So we're going to be assuming that the car is initially moving up the hill. So it's going to have like a VI, if you will. And then it's going to come to a stop at position B where velocity would be 0. And we're specifying that the engine is turned off, the car's in neutral, and there's no friction. So engine turned off, meaning we're not worried about any loss of thermal energy, or we're not going to have some other work done to our system. And the car is free to roll because it's in neutral. So in the beginning, as it's coasting up the hill, we're imagining a ball rolling up the hill and you let go of it. It's going to have all kinetic energy in the beginning. That's where it's moving the fastest. In the end, it's going to have all gravitational at that moment that it stops. And that makes our equation pretty simple. So now we're going to change that up in part 2B. So we're now going to include friction. So with friction comes thermal energy. So it's going to look the same as 2A, but now we're going to have a little bit of thermal energy. So not much really changed there. In 3, we now add a person to our system where they're going to be pushing the car up. So if we define our system as the car, the road, and the earth, and everything starts off at the bottom of the hill, so no velocity, so VA is 0, so it's at rest. And then it goes to position B, where it's going to be at rest, but it's at a greater height. and the person's tired. But since we're not including the person in our system, we can include the energy from the person. So that's where the energy starts. That's how the cart begins to move up the hill. So that wouldn't make sense to have no energy unless we remove it from the system. So anytime where you want to assign energy to an object of our situation or our system, and that object's not in our system, that means work has to be done on the system. So the person is going to do work on our system. So that's where it would change from being energy in the beginning to work. And we're including friction here because the person would not be able to, it doesn't clearly come out and say that we're including friction, but the person would not be able to push the car up the hill if there was not friction, so there has to be some type of thermal energy from friction. In 3B, now we're including the person. So what kind of energy does the person have? It's not like a physics type energy. It's not elastic potential, gravitational potential, or kinetic, but rather yet it's going to be ECH, which we're going to refer to that as chemical potential energy stored in your body as fats. So not necessarily a physics type equation, but we can set up a qualitative equation. And that's why in that first part, we defined it as work and not energy, because it's a physics class and it's chemical potential energy. In 4A, we have a spring that's loaded here, and there's a bunch of bricks on top, and they're at some initial velocity of 0 and height 0, and then the spring is going to get released, and the bricks are going to go upward, moving at some velocity at some height greater than 0. We're doing this without friction, and we're including everything in our system. So it starts off all elastic potential energy stored in our spring, and that goes into kinetic and gravitational. So since it's a height above the ground, it's got gravitational. Since it's still moving velocity greater than 0, it still has kinetic. If it wasn't moving anymore, it came to its peak, as high as it would go, then that kinetic would drop out. So now we're going to include friction. So in that problem, when you might be thinking, well, where's the friction going to exist? There's no object moving past each other. But there is internal friction in the spring itself. As those particles bend and compress and move, that does create a thermal energy that we're now including and taking account for. In 4C, we're now removing the spring from our system, which that's where all the energy starts. So that's a little clue that we're not going to have anything in our bar graph. So that's a clue that we need to include work. So work is going to be added to the system, or some object, in this case the spring, is going to do work on our system. In 5, we have yet another spring and crate, or a bunch of bricks, and they're going to go up the hill. So hopefully you're recognizing some patterns as we go from scenario to scenario now. So we're including everything, frictionless, so no thermal. We start with that elastic in the spring, and then at position B, it's now some height, and it is still moving. So it's moving, so it has kinetic, and it's some height above initial 0, so it's got gravitational. In B, now we're including friction and not including the spring, so 2 changes at once. So by removing the spring, we need to make sure, specify that there needs to be work done on the system. By including friction, there's going to be thermal energy to account for as well. In 6, we have a bungee jumper. In scenario A, we're including everything. We're assuming it's a frictionless system. And I need to erase that because I accidentally put that in there. So frictionless system. There you go. So we're starting in all gravitational stored up on the cliff. And then the jumper jumps where it's now above ground. We've still got some space to go here. But we have stretched out the bungee cord all the way, and we came to a stop to where we're going to start to go back up. Or maybe they're just finally at rest there at the end. So we're still some height above the ground, so we have some gravitational. And there's a lot of energy stored in that elastic band stretched out. 6, if the cord is not part of our system, well, in the end is where the cord was storing it as elastic potential, right? So if we remove that, it seems like there's energy that got lost someplace. So this is where, or the first example, we're seeing that there's work out. Work is going to leave our system. This is why they call it working out when you go to a gym and you move mass around, because the work is out of the system. Usually we think of the system being our human body, so we're leaving it in the gym. And that's it. Again, this was just a brief overview. If you need specifics on some of these videos, feel free to look in Schoology for the detailed descriptions.